So this is exercise 4G, another look at sums of a geometric sequence, but this time we're going to look at something called the sum to infinity. And we've actually got a picture of this here which kind of tries to explain what this means. So if you start with a half of this square, for instance, and I add it to a quarter, you can see how they've got the quarter. They've obviously halved the half and got a quarter, and then you half the half of the half and you get an eighth. And if I keep on adding all these things up, there's a 16th, and there's a 32th, if there is such a thing, and you keep adding all these things up and up and up and up, and you'll notice a 64 for 1/28, 1/256, presumably that one there is a 1 over 512, and that one is a 1 over 1024th, and they just get silly and silly. But the point being, you can keep on halving whatever's left, and they keep on halving, and you carry on adding on an increasingly small amount. Now, the whole point about this is we know what this symbol adds up to. It definitely equals 1 whole square, so it equals a whole one. But you wouldn't think that a half plus a quarter plus an eighth plus a this and a this and a this and a this and forever and ever would equal a nice number like that. But it does. It adds up to a whole one. And that's a new idea for us, really. Let's just have a little starter before I get properly into that. We've got 3 and 6 and 12 and 24. I want to know, when does it first get bigger than 100,000? Now, this is geometric series. It says the sum of geometric series, which we saw in the last lesson video. We use this formula, so I'm just going to do it. The sum of I see, the sum of n terms equals a, which is 3, 1 minus r. Well, r, of course, is a term divided by the one before it, which is clearly 2. So 1 minus 2 to the power of n over 1 minus 2, and we want this to be bigger than 100,000. Now, I did say to you last time, you might as well just call that equals 2 and just adjust your answer afterwards. I think that's easier. So if I do this 1 minus 2, I'm just realizing perhaps I should. It's not so obvious here, actually. So I'm going to write, we want it to be bigger than, and I'll show you why I'm writing that. So first thing I want to do is I'm going to, 1 minus 2 is minus 1, so I'm going to move the minus 1 over, and it becomes this. Now, when I move the minus 1 over, I have to change the sign because I'm timesing by minus 1. So I get minus 100,000. And I can move the 3 over and divide by the 3. That gives me 1 minus 2 to the n is minus 100,000 over the 3. Yeah, might as well leave it like that. And now what I'm going to do is I'm going to move that over there, which would give me, I'm only adding it on, so it's 1 is less than that minus 100,000 over the 3 plus 2 to the n. And now I'm going to move that over there, so that's not a very nice number. So I'm just going to do that. It's 1 plus 100,000. I think we've got there enough zeros. And I get 1 0 0, 4 zeros in total, over 3 is less than 2 to the n. And of course that means 2 to the n is more than that number. And therefore n is more than the log to the base 2 of that number. N is more than, so I'm going to log that number to the base 2, log base 2 of the answer equals, and I get 15 and a bit. So n is more than 15.02, so I'm going to assume that n is 16. Yes, 16, only just the 16th term. So now we've seen that, let's have a look at this. So it says find the sums of these answers. So if we just type these in using the formula that we had down here, the first one is 1 for the a. 1 minus, what is the r here? R is a half divided by 1, and so you can see that is a half. So it's 1 minus a half to the power of 5 divided by 1 minus a half. So for the first one, I get 1 minus 0.5 to the power of 5, and I divide by 0.5, and I get 31 over 16. And if I press the SD button, I get 1.9375. I'm going to do the same for S10 over here. Well, that's 1 times by the bracket 1 minus a half to the power of 10 over 1 minus a half. So you can see it's almost identical. So and I get 1.998. And you start thinking to yourself, hang on, there's a pattern here. That was 5 terms, this is 10 terms. Now let's do 15 terms. I'm typing it in now. 1 minus a half to the power of 20 this time. And divided by a half on the bottom. I get lots of 9s now. 1.9998093. And it's not hard to then think to yourself, well, you know what, if I had 100 terms, I reckon it's going to not be close to this 2 value, which this is obviously approaching. I think it's going to be equal to 2. And that's what you're meant to surmise. So when you get this, you basically, if it gets closer and closer to 2, the partial word for that is converges, and you can see each of these sums after one term is just equal to 1, and then it's 1.5, and then it's 1.75, 1.9 odd, and you can see it gets closer and closer and closer, and you, perhaps not surprisingly, this in due course gets so close to that that it actually hits, well, it never actually hits the line, but you know, nominally at infinity it will hit. So we are able to give you a formula now for the sum to infinity of a geometric sequence, and it's a over 1 minus r. Notice this only works when r is less than 1. In our very first example, where we had r equal to 2, then it's going to get bigger and bigger and bigger. This works because effectively, whenever r is less than 1, or I should really say mod r is less than 1, because if it was equal to, say, minus 0.2, the same thing happens. If the r value is so small that effectively the terms are getting smaller each time that you add on, then eventually you add in on nothing. That's the logic, so it doesn't change. So a couple of examples here. It says find the sum to infinity of these. So very first job, find r. It's 7 over 21. So that's a third. Now notice that fits that rule. R is less than 1. So therefore I can find the sum to infinity. And it's a, what's a? It's 21. Divided by 1 minus r, 1 minus a third, which is obviously 2/3. So I've got to do on my calculator. 21 divided by 2/3, and I get 63 over 2, or 31.5. Don't mind which you write. Second one, find the sum to infinity. What is it here? So I find my r. 6 divided by 3, 6 divided by 3 is 2, and therefore it's too big. It doesn't fit this rule. So I don't think there is a sum to infinity. And good, it does say there's no sum to infinity. So, I've got 31.5 on mine. That's, if I just typed it in wrong, I suspect I have. 21 minus, yes, I think it's just a mistake on my part when I just typed it in just now. So another example, for the following geometric sequence or series, write down the value of the common ratio. Well, that's easy to do. So r equals, this time it's minus a half divided by 2. So I think I get minus a quarter. Now notice that fits the mod r is less than 1 rule. A quarter is definitely less than 1. Ignore the minus sign, it's definitely 1. So we can find a sum to infinity, because it does converge. And what does it converge to? Well, we're just about to find out. Sum to infinity is a over 1 minus r. There you go. 2 over 1 minus a minus a quarter. So that's 2 over, effectively 5 over 4. And that will give me, I turn it upside down and multiply, I reckon that gives me 8/5 or 1.6. 1.6, yes. Ding. Summation notation, then just be aware that sometimes you get asked to do certain sums on the calculator, or rather on an exam, and it's tempting to use the calculator button, but if they use this magic phrase, don't they, use detailed reasoning, this is how OCR signal to you, you better show some working out. So let's assume from now on this exercise we're going to use detailed reasoning. Whoops, it won't. So here's an example. It says find this. Now there is, if you look on your calculator, a button that does it. Obviously it doesn't have the infinity button on it, so that should warn you, be careful. I'm going to just work out what each term is first of all. What's my U1 term? It's 4 times 0.2, and it says n plus 2, so that's to the power 3. So I just do that on my calculator. 4 times 0.2 cubed. I get 4 over 125. Okay, that's my U1. U2, well actually this is just 4 times 0.2 to the 4 now. So I'll just write this down. 4 times 0.2, because it says it's 0. To the 4, sorry. 0.2 to the 4. So really all I've done is I've times there to there by 0.2, and so I've got the answer 4 over 625. I suppose I need my R value, so it's 4 over 625 divided by 4 over 125. And if you listen to what I said just now, it shouldn't surprise you to learn that that's 0.2, because really all we've done is we've added a power to 0.2. So is R less than, or mod R less than 1? Clearly yes it is. So I can find the sum to infinity. Sum to infinity is A over 1 minus R equals A. What's A is this 4 over 125, and I'm dividing by 1 minus the 0.2. So 4 divided by 125, and I've got to divide that answer by 1 minus 0.2, and I get a 25th. Sum to infinity is a 25th. See if I agreed with that before. Yeah, a 25th, 0.04. So that's worked out quite nicely. A little exercise, a couple of questions. Find the following geometric series. It's like the one I've just been doing, I suppose. Your first job is to work out R. So R equals the minus 3 divided by 2. That's immediately equal to minus 1.5, which is greater than 1. Is if I modulus of it is greater than 1, and therefore no sum. So no sum to infinity. What's this one? It's R equals minus 1 divided by 3. Oh, that's okay. So the sum to infinity is A over 1 minus R is 3 divided by 1 minus a third, which is 3 divided by 4 thirds, which is 3 times by 3 over 4, which is 9 over 4. So that one does, and according to me, 2.25. Perfect. So you're going to do a few questions on this, exercise 4G. There's 2 more exercises to come on this. Exercise 4H basically looks at harder problems. And then we've got a revision of all things, sequences, both year 12 and year 13 sequences all of a sudden. So this should be a relatively nice exercise again. It's a nice formula. Just be looking out for whether or not the sum to infinity actually exists, because sometimes they don't. Best of luck.